Welcome back to our DP-600 exam preparation series. This is part 3 of 4, where we're diving into the performance aspects of Microsoft Fabric. If you're new here, I recommend starting with parts 1 and 2 for a complete understanding of the certification requirements. Here's what we're covering today. First, we'll explore how to use the monitoring hub to diagnose performance issues. Then, we'll optimize a data flow together, cutting its runtime significantly. Finally, we'll tackle delta table partitioning and V-order optimization, topics that frequently appear on the exam but are often misunderstood. By the end of this V-podcast, you'll have mastered the performance optimization techniques tested in the DP-600 certification. What's slowing you down? Identifying pain points. Why does troubleshooting your Microsoft Fabric setup often feel like finding a needle in a haystack? 1 minute, everything seems to be running smoothly, and the next, a performance issue surfaces without clear warnings, leaving you scrolling endlessly through logs or staring at graphs that don't seem to add up. This is where the monitoring hub comes in, offering a central place to get a complete view of your data operations. But while it's packed with insights, figuring out what's worth your attention can quickly feel overwhelming. Let's start here. The monitoring hub isn't just another dashboard. It's specifically designed to give you actionable insights into the operations within your Fabric environment. Whether it's a refresh failure in a semantic model, a processing issue with Spark notebooks, or a delay in your data flow, the monitoring hub acts as a command center for identifying the problem. But as useful as it is, it's not about looking at every single metric available. That's where many users trip up. Knowing which numbers truly impact performance and how they interact is the key to getting meaningful results. Let's consider one of the most important metrics, capacity units spent. This value tells you how much of your allocated resources specific operations are consuming. Maybe you're running multiple data flows simultaneously, and the capacity unit spend is unusually high, inching toward throttling territory. Ignoring this could mean more than just slower pipelines. You could experience outright refresh failures if overuse persists. Then there's throttling itself, a metric every analytics engineer should keep an eye on. Throttling isn't just about limits. It's a signal that you need to rethink workloads or scale your capacity. Together, these metrics form the backbone of effective performance monitoring, especially when combined with specific information about refresh failures or completed jobs. Imagine this. You're dealing with a data flow that takes over an hour to complete, far longer than expected. At first glance, you might assume the error is happening at the source system or that the query design is too complex. That's the default assumption most people jump to, checking external systems instead of digging deeper into the available insights. With the monitoring hub, it's easier to see where the slowdown is happening, but only if you know which details to check. In this case, examining the refresh history within the hub would show a particular step with excessive processing time, a data type conversion error, for instance. Without that focus, you spend days chasing the wrong cause, like network bottlenecks or storage issues, which only delays resolution further. This is why understanding the right metrics is the real first step toward optimization. Data flows that underperform often do so because key metrics like refresh errors or resource consumption haven't been monitored consistently. But once you isolate the correct signals, the problem shifts from solving endless puzzles to acting on targeted insights. For example, let's say your refresh history pinpoints a transformation step as the culprit. Optimizing that one segment speeds everything along without needing a total overhaul. And what about those resource-heavy processes that strain your capacity? The Capacity Metrics app is another critical tool that complements the monitoring hub by providing a high-level overview of how your environment uses resources. It doesn't just tell you that something is slow or that capacity is limited, it breaks down where that usage is happening. Are Spark notebooks eating up more compute than expected? Is storage growing at an unsustainable pace? It's all mapped out in this app, showing trends over time and isolating specific resource drains. By comparing these insights with the granular data in the monitoring hub, you create a full picture of both the high-level status and the details of individual processes. For many users, the sheer volume of available logs and metrics in Fabric is what makes troubleshooting so daunting. Think of it this way. If every warning and data point looks equally urgent, it's hard to know where to start. That's why focusing on capacity unit spend, throttling, and refresh failures simplifies your troubleshooting process significantly. Each of these metrics tells a specific story about resource allocation, system stress, and workload efficiency. You no longer need to search through non-essential details or make guesses. This data gives you observable actions to take. Let's go back to our earlier example of a slow data flow. Maybe it failed repeatedly due to a timeout error. Without checking the refresh history or capacity metrics, you could assume the problem lies in database connectivity or bad queries, spending hours testing theories. In reality, the refresh history would immediately show you that a join operation within your transformation is unexpectedly consuming resources. Or perhaps the capacity metrics app tells you throttling was triggered during that period. Those clues direct you straight to the solution, optimizing the join or scaling your capacity temporarily until the workload becomes more manageable. It's a game changer. And this isn't just about finding the problem faster. It's about making troubleshooting repeatable. While every issue might have a unique context, narrowing down investigations to a smaller set of meaningful metrics gives you a process you can rely on. The next time something slows down, you already know where to look, how to interpret the patterns, and which results lead to sustainable improvement. Even with the right tools and metrics in hand, though, diagnostics are only half the battle. If the monitoring hub tells you what's wrong, you still need to fix it. And the fixes aren't always about rewriting entire pipelines or rebuilding from scratch. That's the topic we'll tackle next. Actionable strategies like staging tables and fast copy that can take a sluggish operation and cut its runtime by half. Because knowing the numbers helps, but real performance boosts require smart optimizations. Fixing data flows, staging tables, and fast copy. What if a one-time setup could slash your data flow runtime by half? It sounds too good to be true, but staging tables paired with features like fast copy can turn this into a practical reality. Data flows are a workhorse when it comes to moving and transforming data in Microsoft Fabric, but they're also a common source of frustration. You might already have carefully planned out your transformations, yet the runtime drags on. This leaves you wondering if something fundamental has been overlooked. The good news is that the solution often lies not in rethinking the transformations themselves, but in how intermediate data is managed behind the scenes. Staging tables are a foundational optimization tool in this process, and they work by addressing one of the major inefficiencies in standard data flows, the overwhelming burden placed on the Mashup engine. When staging is disabled, the Mashup engine takes care of the entire process, from start to finish, which can strain resources, especially when handling a large dataset or performing numerous transformations. Instead, staging tables allow you to split the workflow into manageable steps by offloading intermediate data into lakehouse storage. From there, the Spark engine takes over, efficiently processing those transformations before sending the final outputs downstream. This approach leverages the strengths of both systems, reducing overall runtime by taking full advantage of Spark's ability to handle massive data volumes. But why does the Mashup engine alone tend to falter? The Mashup engine is excellent for smaller workloads or simpler transformations, but its efficiency drops off considerably as the complexity of the task increases. For instance, think of a data flow that needs to join multiple tables, apply specific filters, and create new calculated fields. Without staging, all of the intermediate results are stored and processed entirely within the Mashup engine, which wasn't designed for such heavy lifting. Staging tables shift these intermediate steps to external storage, spreading the workload in a way that's far more scalable. Here's how it works, step by step. First, you configure your data flow to write its intermediate outputs to a lakehouse staging table. This effectively creates a checkpoint, capturing the data at this transitional state. Next, the Spark engine processes the transformations against the staged data, which is now optimized for faster computations due to Spark's ability to work with distributed data. Finally, after the transformations are complete, the results are either pushed into another staging table or sent directly to their final destination, depending on the requirements of the data flow. You've essentially broken a long and complex operation into smaller, more optimized steps without losing any of the functionality or accuracy. Now let's look at this in a real-world example. Say you're running a data flow that consolidates sales data from multiple regions. The raw data comes from several disparate systems, each with slight variances in column structure and naming conventions. Before merging these tables into a final model, you need to standardize the column names, strip out unnecessary fields, and create a derived column for year-over-year performance comparison. Without staging, the system tries to handle these tasks all at once, overloading the Mashup engine. Even if the data flow eventually completes, it might take upwards of an hour, and that's assuming no errors occur along the way. Enabling staging changes the equation entirely. As soon as you configure the data flow to use a staging table, the raw data from each source system is first written to the lakehouse. From there, the Spark engine processes the data, renaming the columns, applying transformations, and calculating the derived fields. By breaking down the operations like this, the runtime can drop from an hour to as little as 20 or 30 minutes, depending on the size of the dataset. Any future changes to the flow, such as adding a new column, can also be implemented more easily, as you're now working with clearly segmented operations. While staging tables focus on optimizing transformations, fast copy tackles inefficiencies specific to data movement. Fast copy is a relatively new feature in Microsoft Fabric that shares the underlying technology of the data pipeline copy activity. It is designed to minimize transfer delays, particularly for scenarios where large amounts of data need to be moved between systems. Imagine a situation where your pipeline processes terabytes of data daily. Even if your transformations are perfectly optimized, the act of simply moving this data can create delays significant enough to negate those gains. By enabling fast copy, you're essentially prioritizing the speed of data transfer, allowing the rest of the pipeline to proceed without bottlenecks. Fast copy is simple to implement but makes a noticeable difference when applied to workflows that manage high data volumes or frequently updated systems. Let's revisit the earlier example of the sales data. If the consolidated data needs to be transferred between multiple regions after processing, fast copy ensures the data movement itself isn't adding unnecessary delays. It reduces the potential for bottlenecks that might otherwise occur when moving large tables to and from the lakehouse or other storage destinations. By combining staging tables with fast copy, you've addressed both transformation and transfer inefficiencies, resulting in a far more streamlined process. There's also an important relationship between the two. Staging tables not only prepare your data for easier transfer, but often work better when paired with fast copy, as the transfer step benefits from the streamlined intermediate outputs. It's not a feature that's explicitly tied to staging, but the two complement each other well when used together. Results speak louder than processes, so what happens when these techniques are applied? In one test case, a retailer's data flow initially took just under 4 hours to process their daily sales data. After introducing a two-step staging table approach and incorporating fast copy, the runtime was reduced to just over 1 hour. Key calculations, which previously lagged due to system overload, were particularly impacted by the shift to Spark processing. The use of fast copy further ensured that once each transformation step was complete, the data promptly moved to the next stage, maintaining the pace. Such significant improvements demonstrate the tangible value of taking a step back and assessing where the bottlenecks lie, whether it's in computation, transfer, or both. The time savings cascade throughout the entire system, allowing downstream models, reports, or dashboards to update faster than previously possible. And when we think about enterprise-grade operations where time really means money, these changes can result in notable cost savings due to reduced resource usage and optimized capacity. Before we completely move forward, it's important to address one misconception. Some users assume that enabling staging might introduce unnecessary complexity into their workflows. After all, it adds an extra layer to the process. But staging tables don't exist to complicate. They exist to solve. They allow you to stop thinking about the strain on your Mashup engine and shift the hardest work to a more efficient processor. This approach also doesn't lock you into rigid operational changes. If you find that staging doesn't deliver the results you hoped for in a particular workflow, it's simple to disable and revert to your previous setup without permanent impacts. It's all about finding the balance that works for your specific environment. Fast copy, while still in preview, is another feature that might not have broad deployment just yet. But for users with early access, it provides an added layer of flexibility for experimentation. Don't think of it as a separate decision from staging. Instead, see it as a tool that complements the effort to reduce runtime and avoid transfer-related delays. As both features continue to evolve within the Microsoft Fabric ecosystem, it's likely that they'll become a standard recommendation for anyone working with large data flows moving forward. These tools are a reminder that performance isn't just about what you do to the data. It's also about how you manage what happens between each step. Of course, even with optimized data flows, your SQL processing can become a bottleneck if it isn't adjusted properly. Writing faster queries and finding inefficiencies in execution require an entirely different set of tools. That's where dynamic management views, or DMVs, and query insights come into play. These tools don't just process your queries, they make them fly. So if you've cleaned up your data flows, but your SQL is lagging behind, stick around. There's a lot more we're about to uncover. SQL queries that fly, optimizing with DMVs and query insights. Are your SQL queries secretly sabotaging your performance? It's not uncommon to come across queries that run much longer than expected, grinding your workflow to a halt for reasons that aren't immediately obvious. Even when best practices are applied, it can feel like some queries simply refuse to cooperate, leaving you questioning the root cause. This is exactly where dynamic management views, or DMVs, and query insights come into play. Together, these tools provide a clear window into what's slowing your queries down and how you can optimize them for better performance. Dynamic management views are the gateway to understanding live query performance at a granular level. They're built into Microsoft Fabric and exist under the CS schema, offering detailed snapshots of query activity, session states, resource usage, and connection details. Think of DMVs as your backstage pass to the inner workings of the SQL engine, showing you everything from session IDs to which queries are consuming the most resources. The key is that DMVs not only provide data about what's happening now, but reveal patterns that can guide your optimization strategy. The frustration of long-running queries often stems from not knowing where to look first. When a query lags well past its expected runtime, the instinct might be to inspect the query text or rethink indexes. While valid steps, they don't provide the full context. DMVs give you that broader view, starting with a fundamental understanding of connections, sessions, and requests. These three components are at the heart of how queries are processed in Microsoft Fabric. A single session represents the instance where a user is connected to the SQL database. Each session links to a connection, and a connection can have multiple requests or queries running at the same time. By identifying whether the issue lies within a session, connection, or specific request, you can quickly narrow your focus. For example, let's say you're dealing with a report that's taking far too long to refresh. You open the DMVs, starting with exec sessions, to see which active sessions are linked to the issue. Immediately, you notice that a particular session has been running for hours, far longer than usual. Switching to exec requests, you drill into the request details and spot it. A query joining multiple large tables without efficient filtering. You've just moved past guessing and have tangible data pointing directly to the problem. But while DMVs give you the raw data, they don't necessarily offer a prepackaged solution. That's where query insights become an indispensable tool. Query insights provide a user-friendly abstraction layer over the DMVs, simplifying performance monitoring through predefined views like frequently run queries and long-running queries. These views essentially do the hard work for you by aggregating and summarizing the most important details. For instance, if you check the long-running queries view, you'll get a straightforward list highlighting the queries that consume the most time to execute. It's a much faster way to identify bottlenecks compared to manually piecing together DMV data. Let's walk through a concrete example to illustrate how these tools work together and transform your optimization process. Imagine you're tasked with optimizing a financial report. Connected to a SQL-backed dataset, this report has a critical query that's notorious for its runtime, clocking in at over 18 minutes on average. You start with DMVs to get a sense of what's happening under the hood. By querying exec requests, you pull the detailed execution stats and notice that this query consistently spikes the percentage of CPU usage during its runtime. Digging deeper into the query text itself, you find multiple nested subqueries and a lack of proper where clause filtering. Rather than aiming for an immediate fix, you decide to cross-check your findings with query insights. Pulling data from the frequently run queries view, you see this problematic query doesn't just run in your financial report. It's also being triggered by other workflows in separate scenarios. What's worse, the query touches millions of rows of transactional data, despite only outputting aggregate results needed for simple calculations. The insight is clear. Before addressing the report itself, the query needs fundamental changes to reduce its data footprint. Now comes the optimization. Starting with the queries from clause, you reduce the number of columns retrieved by selecting only the ones needed for the financial report. From there, you refine the where clauses to filter out unnecessary data early on. Subqueries are replaced with joins to improve lookup efficiency, allowing SQL to process the data in a more streamlined way. When you rerun the optimized query, the results are immediate. The runtime drops from 18 minutes to just under 2 minutes. A change that's reflected not just in the report, but across every workflow that uses the same query structure. At this point, you might ask, why not skip to Query Insights directly if they're so much more user-friendly? While Query Insights provide accessible summaries, they rely on the groundwork laid by DMVs. DMVs offer the granular information you need to diagnose deeper problems like session timeouts or excessive resource consumption during query execution. It's the combination of both tools, raw detail from DMVs and actionable summaries from Query Insights, that gives you the full edge in SQL optimization. The real-world impact of these optimizations isn't just noticeable in runtime improvements. Reducing the load on individual queries also has a cascading benefit. Lower storage I/O, reduced CPU stress, and improved availability for other operations. If we look back to our example, optimizing that financial report query meant releasing critical resources sooner, which in turn allowed dashboards downstream in Power BI to refresh automatically without delays. Over time, this proactive approach can lead to measurable gains in overall system stability and user satisfaction. There's another key advantage worth stressing here. SQL optimization isn't just about making each query run faster. It's about fostering a consistent approach to building well-performing systems. Often, poorly written queries are the result of an incomplete understanding of how SQL engines process requests. Tools like DMVs and Query Insights serve as both a guide and a learning opportunity. By visualizing bottlenecks at every step, users not only fix current issues but also pick up better practices along the way, reducing the likelihood of similar problems popping up in future workflows. However, even when every query is fully optimized, there's still one critical dependency that can undermine performance: the underlying delta tables. If the structure of these tables isn't designed with performance in mind, no amount of query tuning is going to deliver the results you're looking for. This is especially true when it comes to partitioning, a common feature that, when used properly, can dramatically speed up data retrieval but has the potential to backfire when misunderstood. You might think smaller partitions always lead to faster performance, but that's not always the case. Without careful design, excessive partitioning can result in too many small files, which slows down both reads and writes. Fixing this involves rethinking how you approach partition strategies, and that's exactly what we're diving into next. We'll cover the myths surrounding delta table partitioning, identify common pitfalls, and give you the techniques to build delta tables that stay efficient even as your datasets scale. Debunking delta table myths. Partitioning done right. Think smaller files equal better performance. Think again. While partitioning delta tables is often at the heart of optimization strategies, it's also one of the most misunderstood areas of data management. On the surface, breaking large files into smaller, more manageable chunks seems like a universal win, right? Smaller file sizes should lead to faster read and write times, better processing efficiency, and overall improved performance. But here's the catch. Not all partitioning is created equal. Poor decisions in partitioning, especially when based on high cardinality columns or default settings, can wreak havoc by overloading your system with excessive small files. Let's unravel some of the common misconceptions and turn partitioning into the powerful tool it's designed to be. Partitioning, for those unfamiliar, is the process of organizing your delta table data into segments or partitions based on the values in a specified column. These partitions allow Spark, the underlying processing engine in Microsoft Fabric, to parallelize operations. Instead of scanning through an entire giant table, Spark can focus on just the relevant partitions, saving substantial time during queries or transformations. But here's where it gets tricky. The way you choose to partition your data can make or break this process. Too many partitions, especially with tiny files, overwhelm Spark with file open and close operations. Too few partitions result in massive files that can't take full advantage of parallel processing. The number one rule when designing your partitions is to pay close attention to cardinality. Cardinality refers to the number of unique values in a column. A high cardinality column, like user IDs or unique transaction numbers, is rarely ideal for partitioning. Imagine a dataset with 1,000,000 rows, and each row has a unique user ID. Partitioning on that column would result in 1,000,000 tiny partitions, creating what's known as the small file problem. Each small file has overhead costs associated with metadata operations, slowing down not only reads but also writes. Instead of speeding things up, you've just added significant inefficiency to your pipeline. Let's think about a different scenario, partitioning by a low cardinality column like region or year. This approach works far better because it creates a manageable number of partitions that align with logical groupings in the data. For example, if you partition by year in a dataset covering the past decade, you'll end up with 10 partitions, each handling a substantial chunk of data. Spark can process these partitions in parallel without the same overhead issues, striking a balance between speed and efficiency. One of the most common use cases for partitioning is with time series data that includes date or timestamp columns. In many datasets, events or transactions are naturally grouped around specific time periods like months or years. By choosing a time-based column for partitioning, you can structure your data in a way that matches how it's most often queried. For instance, if your analysis involves monthly sales reports, partitioning by year and month ensures that only the necessary data for the selected time frame is scanned. However, over-partitioning, even in this logical structure, remains a risk, such as breaking data down into daily partitions unnecessarily. To put this into perspective, let's look at a practical example involving airline data. A Packet file containing 1,000,000 rows of flight information is loaded into a lakehouse without any partitioning. All the data is stored in a single file. When queried, Spark is forced to scan this massive file, slowing the operation. Now, let's try again, but this time we partition the data by year and month. This creates a more efficient setup with fewer files, allowing Spark to skip irrelevant partitions based on the query conditions. Finally, consider an over-partitioned scenario where data is broken by year, month, and day. Instead of improving performance, this choice generates 59 small files, increasing the overhead and hurting performance. The difference between these approaches is clear when we inspect the tables using Spark's describe detail method, which reveals their partition configurations. The first table has no partitions, storing all data in a single file. The second uses year and month as partition columns, resulting in 2 Parquet files optimized for access. The final, overly partitioned table fragments the data into dozens of files, underlining the importance of striking the right balance. While partitions enable faster reads by leveraging parallelism, inefficiencies creep in when the focus shifts from optimal processing to managing an unnecessary number of files. You might be wondering where to draw the line when considering partition sizes. A good benchmark is to aim for roughly 1 GB of data per partition. This size ensures that partitions aren't too small to cause metadata overhead, or too large to limit Spark's ability to split the workload across available executors. For smaller datasets, 1 or 2 partitions may suffice. But as data scales, maintaining partitions around the 1 GB mark helps keep operations efficient without overwhelming the system. This guideline also supports smoother write operations, since Spark can handle partitioned write tasks more predictably when files are manageable. Another practical tip involves auditing your Delta table's partition configuration regularly, especially as your dataset grows. With tools like Fabric's SQL capabilities or Spark's inspection methods, you can quickly check the size and number of partition files associated with a table. If you notice a significant drift toward an excessive number of small files, or worse, unreasonably large partitions, it's time to rethink your strategy. For instance, breaking a partitioned column with 5 or 6 values into smaller categories might seem practical initially, but as your table grows and those dimensions expand, the resulting fragments create new bottlenecks. So, what happens when you get it right? Thoughtful partitioning can make a dramatic difference in both read and write performance. Let's revisit the airline data example. Initially, storing all rows in one massive file resulted in sluggish query performance, with Spark unable to leverage parallel processing. Applying year and month partitioning reduced query times nearly threefold, as irrelevant partitions could immediately be skipped during a search. The workload shifted from scanning the entire dataset to targeting smaller focused segments. Meanwhile, over-partitioning, adding day into the structure, caused query times to shoot back up due to the overhead of handling so many small files. This clear performance shift demonstrates how a balanced approach maximizes efficiency without tipping into counterproductive fragmentation. Partitioning isn't just beneficial for queries, though. It also matters for write operations. When delta tables are first created or appended, Spark spreads data across partitions as defined. Good partitioning practices ensure that write operations proceed quickly and predictably. Poor partitioning, on the other hand, compounds the complexity, with small files taking longer to write due to file management overhead. While low cardinality columns and 1 GB partitions form the cornerstone of effective strategies, industry practices also favor a flexible approach tailored to specific datasets. Time series data performs best partitioned by columns like year or month. In comparison, categorical data, such as data segmented by product type or region, benefits from partitions aligned with logical business groupings. This adaptability ensures that partitioning choices align with both the data's natural structure and how teams intend to query it. The performance gains achieved through proper partitioning go beyond immediate technical benefits. They free up resources for additional workloads, helping businesses scale their operations without ballooning the cost of compute power. Efficient partitioning also undergirds more advanced optimization techniques such as caching or pre-aggregations by preparing the data for faster access at the source. For teams managing resource constraints, the cost savings can be just as valuable as the improved performance. But partitioning alone doesn't solve every bottleneck. Even with thoughtful strategies, there's another layer you can apply to your delta tables that completely reshapes how data is read and written. This technique, called V-order optimization, is designed to address the inefficiencies that remain even in well-partitioned tables. Where partitioning focuses on improving efficiency at a macro level by structuring the data logically, V-order optimization restructures the files themselves internally, organizing data within Parquet files for faster access during queries. If you've mastered partitioning but want to push your delta table performance even further, V-order optimization is the logical next step. It's not just about storing your data efficiently across partitions. It's about ensuring that every read or write operation leverages the most efficient internal structure possible. Up next, we'll dive into how V-order works, its unique role in delta table optimization, and how enabling it can significantly boost performance across your workflows. V-order optimization, the hidden hero. What if your delta tables could optimize themselves? That's essentially the promise of V-order optimization, a proprietary feature in Microsoft Fabric that automatically enhances the performance of your Parquet files. Even if your tables are well partitioned, you might notice that read performance, especially for large datasets or complex workloads, doesn't always meet expectations. This is where V-order becomes indispensable. It restructures the internal organization of Parquet files, prioritizing faster reads without you needing to rewrite queries or overhaul partition schemes. And the best part? In most cases, it's enabled by default, delivering its benefits without requiring a single manual adjustment. Let's start with what sets V-order apart. When your data is written to a delta table, V-order applies an algorithm that sorts, compacts, and compresses the files in a way that optimizes them specifically for retrieval operations. This process doesn't alter the Parquet file's compliance with the format standards, meaning these files can still be used with any tools that support standard Parquet files both within and outside Microsoft Fabric. However, the way these files are structured internally gives Fabric engines a significant advantage when querying them, thanks to reduced file scanning and faster data access. Here's why well-partitioned tables alone might not address your performance issues. Partitioning improves how rows of data are stored and accessed at a high level by organizing them into logical groups, but it doesn't control how the rows within each partition are stored physically inside the Parquet files. Without vOrder, these rows could end up in a random order that slows down read operations. Spark has to work harder to locate relevant records, leading to sluggish query performance, particularly when the table grows over time. This creates a bottleneck even in setups where partitions are effectively tuned for size and cardinality. Let's break down the mechanics of how vOrder fixes this problem. When you write data to a delta table with vOrder enabled, it reorders rows and columns within each Parquet file to optimize storage for read-heavy workloads. This restructuring allows Spark to retrieve contiguous blocks of data without wasting resources scanning irrelevant sections of the file. By grouping related data more closely together, the algorithm minimizes the I/O operations needed to satisfy queries. Essentially, vOrder creates a structure that prepares the Parquet files for quicker lookups, reducing both scan time and memory usage. As an example, imagine you're working with an orders table containing millions of rows with a frequent need to filter data by customer or region. Without vOrder, these filters might require the system to read more of the Parquet file than necessary, scanning rows located in non-sequential blocks. But with vOrder, data for each customer or region is stored in a more consolidated manner within the partitions. When a query requests a specific customer's records, Spark can pinpoint the relevant blocks directly, reducing the time it takes to deliver results. Checking whether vOrder is enabled in your environment is straightforward. By default, it's active in the Microsoft Fabric Spark runtime to ensure users benefit from the optimizations without needing any upfront configuration. Whenever a delta table is written, the vOrder algorithm is applied automatically to those Parquet files. But there are cases where you might need to manually confirm or tweak this setting, particularly during troubleshooting or performance testing. To check or modify vOrder settings, you can use Spark configuration properties in your notebook environment. Specifically, the property Spark SQL Parquet vOrder enabled controls whether the feature is active. By default, it's set to true, but if you encounter scenarios where you need to disable it, for example, while testing other optimization strategies, you can set this value to false. Conversely, re-enabling it is as simple as flipping the property back to true. This flexibility allows you to experiment and compare performance under different conditions, something especially useful for advanced users managing highly specialized workloads. The process of enabling or disabling vOrder is quick and doesn't require complex scripting. Here's how you can adjust it. In your Fabric environment, navigate to a Spark notebook tied to your workspace. To check the current status of vOrder, run the following line of code: Python Spark, conf get Spark SQL Parquet vOrder enabled. If the response is true, vOrder is active. If it's disabled, you can enable it by setting the property like this: Python Spark conf set Spark SQL.Parquet vOrder enabled true. And just as easily, you can disable it when needed. Python Spark conf set Spark.SQL Parquet vOrder enabled false. Once you've confirmed vOrder's status, any new data written to delta tables will adhere to the updated configuration. Keep in mind that changes to this property only affect Parquet files written after the adjustment, so existing files won't be retroactively optimized unless they're rewritten. The benefits of enabling vOrder are particularly noticeable for large analytical workloads where speed and efficiency can make or break business operations. Consider this real-world scenario. A logistics company maintains a delta table tracking shipments with millions of records updated daily. Queries to analyze shipment delays by region were taking several minutes to complete, primarily due to high I/O and inefficient file scans. Activating vOrder reduced query times by more than 60%, thanks to faster reads enabled by the optimized Parquet file structure. These performance gains allowed analysts to run more frequent reports, improving decision-making without adding strain to system resources. It's important to note that vOrder optimization does involve some trade-offs. While it significantly enhances read performance, the writing of Parquet files may take slightly longer due to the additional sorting and structuring steps involved. However, this additional processing time is negligible for most use cases compared to the speed improvements during query execution. For scenarios where data is written once but read multiple times, a common pattern in analytics applications, vOrder quickly justifies the upfront investment in write-time processing. One reason vOrder integrates so seamlessly into the Microsoft Fabric ecosystem is its compatibility with the standard Parquet format. While the optimization itself is proprietary to Microsoft, the resulting files retain full interoperability with other systems that support Parquet. This means you can retain the benefits of vOrder even if your data workflows include external tools or platforms. Whether you're working entirely within Fabric or using hybrid setups with third-party systems, you won't need to worry about compatibility issues. Another compelling advantage of vOrder is how easily it complements other Delta table optimization strategies, such as partitioning. While partitioning helps organize data on a macro level, vOrder works at the micro level, optimizing how data within each partition is read and written. Together, these techniques form a powerful combination for improving performance in even the most demanding workloads. Partitioning simplifies the system's ability to locate relevant data, while vOrder ensures that the data itself is stored in a way that further accelerates queries. For organizations managing rapidly growing datasets, vOrder also provides long-term scalability benefits. As tables grow and queries become more complex, maintaining consistent performance often requires frequent re-optimization of data structures. With vOrder enabled, that burden is significantly reduced, as much of the heavy lifting is handled automatically during the write process. This lets teams focus less on manual tuning and more on delivering insights from their data. If we step back and look at the bigger picture, vOrder optimization fits into a broader strategy of Delta table maintenance that also includes regular file compaction and garbage collection. While vOrder addresses the efficiency of read operations, practices like bin compaction through the optimize function ensure that files themselves don't become fragmented over time. Similarly, the vacuum function cleans up unused files, reducing clutter and preserving storage space. Together, these maintenance tasks create an efficient, streamlined system that supports both performance and scalability. Even with all these tactics in play, optimization isn't a one-and-done activity. Over time, as systems evolve and workloads change, keeping your Delta tables in top shape requires consistent attention. Tools like vOrder simplify much of this work, but they're most effective when paired with regular monitoring and maintenance. In the next part, we'll explore how to take Delta table maintenance a step further by regularly running optimize and vacuum commands to consolidate files and free up storage. These aren't just housekeeping tools, they're a critical part of ensuring long-term system reliability and cost-effectiveness. Let's dig into how they work and why they're essential. Delta table maintenance, optimize and vacuum. Can neglected Delta tables really slow your entire pipeline? The short answer is yes, and it happens more often than people realize. Over time, Delta tables accumulate unused files and fragmented data that clog up your workflows, bloating your storage footprint and dragging down performance. What starts as a clean and efficient table can quickly turn into a mess if routine maintenance is ignored. That's why the optimize and vacuum functions are absolutely essential tools for maintaining not just peak performance, but also cost-effective storage in Microsoft Fabric. These tools work together to fight file fragmentation, remove obsolete data, and keep your tables lean and efficient. First, let's talk about the most visible issue here, the proliferation of small files. Whenever a Delta table undergoes frequent write operations, whether it's appending new data or updating existing records, it tends to result in the creation of numerous small Parquet files. Each of these files contains just a fraction of your data, but every single one adds overhead to every read operation. Every time you run a query, the Spark engine needs to scan all these files, open them individually, and manage their metadata. This repeated small file overhead can lead to significant query slowdowns, especially as your dataset scales. The optimize function offers a simple yet powerful solution by consolidating many of these small files into fewer larger ones, a process known as bin compaction. Here's how the optimize function works. Under the hood, it uses the Spark coalesce method to combine partitions without reshuffling the data within them. It's a relatively lightweight operation designed to merge multiple small Parquet files into fewer, larger files. What's great about this method is that it's efficient and idempotent. Once a file is optimized, it won't be reprocessed unless necessary. This means you can run the optimization process repeatedly without wasting time or resources on files that are already in an optimal state. And if you have a table with specific partitions that are accessed more frequently than others, you can target just those partitions rather than re-optimizing the entire table This level of granular control is a huge win for resource efficiency. Now let's see this in action. Imagine you're managing a sales dataset that receives hourly updates. Each update appends a few hundred rows of data, resulting in dozens of small files being added to your Delta table throughout the day. By the end of the week, your table could have thousands of Parquet files, with each file requiring a small but cumulative cost during every query. When you apply the optimize function, it scans those small files, merges them into fewer files approximately 1 GB in size, and updates the Delta log to reflect the new structure. The next time a query runs, the Spark engine only needs to scan a handful of well-organized files, significantly reducing processing time. But optimizing files is only half the battle. What about the stale, unused files left behind after updates or deletes? This is where the vacuum function becomes essential. Every time you make changes to a Delta table, the old files aren't immediately removed. They're retained by default to support time travel and rollback functionality. This is a great feature when managed properly, but if left unchecked, these orphaned files can take up unnecessary storage and slow down your operations. The vacuum function removes these unreferenced files, ensuring that your storage stays clean and cost-effective. By default, Delta tables retain old files for 7 days to allow for time travel queries. However, you can adjust this retention period based on your specific business requirements. For example, if you only need to keep older versions of your data for 1 or 2 days, you can configure vacuum to remove files earlier and save significant storage space. This customization is particularly useful in high-velocity environments where data changes rapidly and keeping weeks of history simply isn't practical. Running the vacuum function is straightforward. To identify and remove unreferenced files, you simply call the vacuum method on your Delta table and specify the retention period. Here's an example command in a Spark notebook. Python Spark. SQL. Vacuum Delta table name, retain 3 hours. This command would delete all files older than 3 hours that are no longer referenced by the Delta table log. However, it's important to approach this step with caution. Reducing the retention period too aggressively can eliminate files that might still be needed for debugging or time travel purposes. As a best practice, align your vacuum schedule with your organization's data retention policy and carefully test any changes to ensure they don't disrupt other processes. Together, the optimize and vacuum functions create a powerful framework for long-term Delta table maintenance. While optimize ensures that active files are consolidated for faster reads, vacuum keeps your tables free of stale and irrelevant data. This combination not only improves query performance but also reduces storage costs by ensuring that you're not paying for space you don't need. Let's step back for a moment and talk about the long-term benefits of these maintenance tasks. First, there's the direct performance boost. Consolidating and cleaning up your Delta tables reduces the strain on Spark, which translates to faster query times and more responsive reports. For example, one dataset processed by an ETL pipeline saw query times drop by over 40% after implementing regular optimized jobs. This type of improvement has real business implications, from more streamlined operations to increased user satisfaction with faster dashboards. Next, there's the cost-saving aspect. Cloud storage costs can quickly add up, especially when dealing with massive datasets that constantly evolve. Regularly running vacuum ensures that you're only paying for the data you actually use, not for the ghosts of files past. This is particularly impactful in environments where storage growth is exponential. Keeping costs in check becomes a key strategy for scaling sustainably. Finally, regular maintenance ensures system stability. Over time, fragmented data and unused files can lead to unpredictable behaviors, such as inconsistent query performance or growing job runtime variability. By making optimize and vacuum part of your routine pipeline, you're minimizing these risks. Think of it like routine car maintenance. You're not only fixing immediate problems, but also preventing future breakdowns. To give you a clearer picture, let's look at a scenario where these strategies are implemented. A retail analytics team managing a Delta table for transactions suffered regular performance slowdowns, with queries taking minutes instead of seconds as their dataset grew. After diagnosing the issue, they implemented monthly optimized jobs and weekly vacuum routines with a 3-day retention period. Within a month, query runtimes were cut in half and storage costs saw a measurable reduction. By proactively maintaining their Delta tables, they ensured long-term reliability and efficiency without constant firefighting. That said, every tool has its limitations, and Delta maintenance is no exception. While vacuum improves storage efficiency, overusing it could interfere with time travel needs. Similarly, optimize won't solve performance issues caused by suboptimal schema designs or poorly written SQL queries. These tasks are part of a broader data management toolkit that also includes partitioning strategies, V-order optimization, and SQL tuning. There's one more benefit worth mentioning: simplicity. These commands are designed to be easy to integrate into existing workflows. Whether you're scheduling automation in Azure Data Factory or triggering maintenance jobs from a Spark notebook, both optimize and vacuum fit seamlessly into standard data processing pipelines. You don't need to overhaul your system, you just need to decide how often to run these commands and let them do the heavy lifting. Maintaining Delta tables isn't just about keeping things clean, it's about future-proofing your system for scalability and ensuring that performance doesn't degrade as your data environment grows. Without regular maintenance, even the best designed tables begin to falter under the weight of compound inefficiencies. By scheduling routine, optimize, and vacuum tasks, you're laying the foundation for a robust and resilient system that supports efficient data processing for years to come. Of course, maintaining your tables is one side of the equation, but choosing the right storage mode for your semantic models is just as important. Whether you opt for import, direct query, or direct lake, your choice impacts everything from query speed to data freshness. In the next section, we'll explore how to make this decision and why balancing these modes could be the key to unlocking better performance in your overall data strategy. Choosing the right storage mode for performance. Is your semantic model holding you back? If you've ever noticed sluggish performance in Power BI reports or felt frustrated by the endless trade-off between speed and data freshness, the storage mode you choose might be playing a bigger role than you think. Power BI offers 3 primary storage modes: import, direct query, and the newer direct lake. Each has strengths, but they also differ fundamentally in how they handle data and impact performance, scalability, and interactivities. So, how do you choose the right one for your needs? Let's start with import mode, the most straightforward and performance-oriented of the 3. In this mode, the data from your source system is fully copied into your Power BI model, ensuring that all queries are processed against this imported dataset. The advantage? Speed. Because the data is already loaded into the Power BI memory cache, this mode enables exceptionally fast queries and interactions, even for larger or more complex dashboards. Every click, filter, and visual is nearly instantaneous because there's no need to make any calls back to the original data source. This makes import mode ideal for scenarios where high user interactivity is critical. Think operational dashboards used by teams that need split-second responsiveness when exploring data, but performance is only part of the picture. The limitations of import mode become evident when you're working with larger datasets or require up-to-date information. Copying data into the Power BI model requires sufficient memory and, more importantly, imposes an upper limit on the amount of data you can handle. This limit isn't just technical, it's practical too. Import mode depends on scheduled refreshes to keep your BI model current, meaning data freshness is inherently constrained by how often you can or are willing to refresh. For small static datasets, this isn't a problem. But suppose your dataset grows into tens or hundreds of gigabytes or requires close to real-time refreshes. In that case, import mode might slow you down more than speed things up. Now, let's contrast this with direct query mode. Instead of copying data, this mode establishes a live connection to your data source, executing queries directly against it whenever a user interacts with the report. This approach ensures that your data is always up to date, pulling the latest values each time a report is refreshed or a filter is changed. If you're operating in industries like retail or logistics, where near real-time reporting is often critical, direct query becomes an invaluable option. Whether it's monitoring daily sales in real time or tracking inventory updates as they happen, direct query ensures that your decisions are always based on the most current data. However, there's a cost to this real-time capability. Since every interaction with your report generates a query to the underlying data source, performance takes a noticeable hit compared to import mode. The speed of your dashboards becomes dependent on the capabilities of your database and network. If the underlying database isn't optimized or queries aren't designed efficiently, users may experience lag or delays with every interaction. This makes direct query less ideal for highly interactive dashboards or when working with complex models requiring multiple joins. Direct queries trade-offs also impact scalability. Because the live connection queries the data source for every report interaction, it can cause increased workload on your backend database, especially as the number of report users grows. While the immediacy of real-time querying is a valuable strength, this mode requires careful thought about the load it places on the source system and whether that system can handle it. So, where does Direct Lake fit in? This newer addition aims to strike a balance between the fast performance of import mode and the real-time data access of direct query. Instead of importing data into Power BI or querying a live database, Direct Lake connects directly to Parquet files stored in a data lake, such as a lakehouse or Fabric's data warehouse. These Parquet files are already optimized for analytics and can be queried efficiently without needing to copy data or rely entirely on a live connection. The key value of Direct Lake lies in its ability to handle massive datasets. Unlike import mode, which struggles with memory constraints, Direct Lake leaves data in its original location without sacrificing query performance. This storage mode is increasingly popular for large analytical workloads where datasets can range from tens to hundreds of gigabytes. Additionally, Direct Lake significantly reduces refresh delays, since it pulls data directly from the source files, which are often updated as part of your larger pipelines. Consider this scenario. You're managing customer behavioral data across multiple channels housed in a lakehouse and updated daily. Using direct query, this setup would introduce query runtime delays, especially for large analytical queries that scan millions of rows. Using import mode, the sheer size of the dataset would exceed the Power BI memory allocation. Direct Lake provides the Goldilocks solution, letting Power BI directly access the Parquet files in their fully optimized state. The result? Faster dashboards that stay connected to updated data without creating bottlenecks. Choosing between these storage modes ultimately depends on your use case. Import mode works best when you need lightning-fast performance for data that doesn't change often or operates within manageable size limits. Direct query is a better fit when real-time data freshness is prioritized, especially for rapidly changing datasets or operational dashboards. Meanwhile, Direct Lake comes into play when handling very large datasets stored in systems like Fabric's Lakehouse, enabling high performance without heavy resource demands on a single user's memory limits. So, how do you decide which one is right for you? Building a decision-making framework can help narrow your choices. Start by asking yourself, how large is the dataset? For datasets under Power BI's memory limits, import mode is usually the favored choice for fast performance. But if the data exceeds those limits or you're managing several gigabytes of rapidly growing information, you'll need to look at Direct Lake. Another key question is how fresh the data needs to be. When freshness is paramount, direct query ensures you're never reliant on outdated imports. But what about mixed requirements? That's where composite models shine. Composite models allow you to combine storage modes in a single report. For example, you could configure fact tables, those large tables updated frequently in your pipeline, with direct query, maintaining real-time responsiveness. At the same time, dimension tables, which rarely change, could sit in import mode for fast interaction. This approach gives you the best of both worlds, timely updates where they matter most and lightning-fast performance for the data that stays static. It also lessens the load on your backend system by reducing the number of live queries sent through direct query. One practical example of a composite model's benefits would be a sales reporting dashboard. Let's say your fact table contains transactional data that updates every 15 minutes, while your dimension tables like product categories or regional hierarchies rarely change. Using direct query for the fact table ensures your dashboard always pulls the latest sales figures. Meanwhile, loading the dimension tables in import mode allows drill-throughs, filtering, or general interactivity to remain lightning fast, as those tables never touch the data source during queries. The combination is seamless and ensures users get the performance they expect without losing out on data freshness. Ultimately, the key takeaway is that no storage mode is inherently better than the rest. Each has its strengths and trade-offs, and your choice should depend on the nature of your data, how your system is built, and what your users need from their reports. Thinking critically about performance, data freshness, and storage limitations will help you make the right selection. And in many cases, combining modes will be your best option. Even the most carefully selected storage mode is only part of the puzzle, though. To truly optimize for performance, you'll need strategies that go beyond mode selection. Strategies like using aggregations and calculated tables. These techniques complement storage modes by ensuring your queries are prepared for the exact needs of the report's users. In the next section, we'll explore how aggregations work alongside composite models to create efficient real-time insights without compromising speed. Let's see how this winning combination can supercharge your reporting workflows. Composite models and aggregations, a winning combo. What if you could have real-time updates and lightning-fast queries? At first, these two goals seem at odds. Real-time data often means slower query performance because you're reaching back to the source with every interaction, while optimized speed traditionally relies on static snapshots of data. This is the classic balancing act that analysts and engineers face when building reports in Power BI. But composite models, paired with aggregations, might just provide the best of both worlds. By mixing connection modes strategically, you can maintain the freshness of live data while keeping queries fast and efficient. Composite models are all about combining different storage modes within the same report. Instead of sticking rigidly to import mode for static, high-speed data or direct query mode for real-time updates, composite models allow you to integrate the two. This mixing of modes gives you a tremendous amount of flexibility. For example, your fact table, the table that holds the bulk of your transactional data, can use direct query to update live from your source. At the same time, your dimension tables, which are often smaller and more static, like product categories or sales regions, can rely on import mode for immediate responsiveness. By configuring your model this way, you avoid overwhelming the underlying database with constant queries while still ensuring users get real-time accuracy where it counts. Here's the challenge: managing real-time needs without sacrificing speed. When you have your fact table in direct query mode, every interaction in your report sends a query back to the data source. For a dataset that grows rapidly, each of these queries can cause bottlenecks, especially if they involve complex calculations or join operations. Your users may start experiencing delays when they try to filter, drill through, or refresh a report. On the other hand, keeping everything in import mode isn't a practical solution for large or frequently updated datasets. You could risk working with stale data or hitting memory size limits, both of which undermine the usefulness of your reports. The key then is finding a strategy that lightens the load on your source system without diminishing interactivity or freshness. That's where aggregations come in. Aggregations work by pre-calculating and storing frequently queried data at a higher level of abstraction, reducing the need for complex on-the-fly calculations. This allows your report to serve results to users more quickly without repeatedly pulling raw data from the fact table. Think of it as creating a cached summary of your data that Power BI can access at lightning speed, while still giving you the option to fall back on direct query for details that aren't already calculated. There are two main types of aggregations in Power BI: user-defined and automatic. With user-defined aggregations, you explicitly specify which columns and summarization types to pre-calculate, such as totals, averages, or counts. This is done using the Manage Aggregations interface in Power BI Desktop, where you map these pre-calculated fields to the original detailed table. For example, a sales report might use an aggregation table to store monthly totals for each product category. If a query asks for overall product sales in January, it will reference this aggregated table instead of scanning millions of rows in the original dataset. Automatic aggregations, available in Power BI Premium, take things further, using machine learning to predict and create optimal aggregations for your data model. These automatic aggregations can analyze user query patterns and suggest pre-calculations based on the most accessed data, saving time and effort in setup. Let's look at a practical example of combining these techniques. Imagine you're building a sales dashboard for a retail business. The fact table contains transactional sales data updated in near real time and stored in your database. With tens of millions of rows spanning years of transactions, this table is easily your largest and most dynamic dataset. It's set to direct query mode, so your reports reflect the most current sales figures, but querying it directly every time a user interacts with the dashboard starts introducing delays. Meanwhile, your dimension tables, like product categories, store locations, or regional sales hierarchies, rarely change. Those can and should sit in import mode for optimal performance and user interactivity. Now let's add aggregation tables into the mix. You create pre-calculated total sales for each product category by day. When users open the sales dashboard and select a time frame, Power BI's engine first looks to the aggregation table for the relevant daily totals. This greatly simplifies the query and speeds up response times. If users later decide to drill down into individual transactions, the model automatically switches back to direct query mode, running a live query against the raw fact table for additional detail. The result is a seamless experience. Whether they're looking for broad trends or fine-grained data, it all feels fast and responsive. This configuration also reduces the load on the underlying database. Depending entirely on direct query for your fact table could overwhelm your system, especially during peak business hours or if hundreds of users are accessing the dashboard at once. Aggregations remove a significant amount of this burden by handling high-level queries themselves, while only the less frequent detailed queries hit the database. The benefits go beyond just speeding up queries. Aggregations improve scalability as your datasets grow in size. Without them, growing query complexity often leads to progressively slower performance. But with a thoughtful aggregation strategy, your reports stay quick and reliable because the bulk of common queries are handled by pre-computed results. And unlike traditional caching methods that depend on fixed data refresh cycles, aggregations in Power BI maintain a dynamic connection to the underlying model. This means that when your source data updates in direct query, the corresponding aggregations can stay in sync, ensuring users always access accurate information without the need for manual intervention. One major advantage of composite models and aggregations is their role in simplifying data models for users. Traditionally, balancing performance with functionality often required workarounds like bridge tables, complicated DAX expressions, or nested calculated tables. Composite models now let you merge multiple storage modes while eliminating the need for these extra layers of complexity. And with support for many-to-many relationships, composite models ensure more natural data connections without performance trade-offs. To see how impactful this combination can be, let's revisit our earlier example of the retail sales dashboard. Before implementing a composite model with aggregations, users frequently reported long loading times when running monthly or quarterly summaries. Every filter adjustment sent a direct query back to the fact table, leading to delays as the database worked through millions of rows. After introducing aggregations, those monthly and quarterly summaries are retrieved directly from the cached totals, cutting query times by more than 80%. Users now experience near instantaneous performance for those high-level views while still having the flexibility to pull transaction-level data on demand. The overall user experience is smoother and database strain is significantly reduced. Critically, this setup isn't static. As data grows or query patterns shift, you can refine your aggregation strategy to remain aligned with business needs. Regularly analyzing which reports are accessed most frequently helps identify opportunities for additional pre-calculated fields. For instance, if a regional manager's weekly reports repeatedly filter sales totals by state, it may be worth introducing a state-level aggregation. Power BI Premium users with access to automatic aggregations benefit even further as the system continuously adjusts and fine-tunes the cache based on usage patterns. Despite their benefits, aggregations aren't a universal solution. For datasets undergoing constant schema changes or extremely granular analyses, setting up aggregations can become complex or even counterproductive. In these cases, alternative strategies like improving source query design, indexing, or using direct lake mode may deliver better results. But when aggregations are a good fit, particularly in combination with composite models, they represent one of the best ways to optimize Power BI performance. The last piece of the puzzle is making sure your storage modes, aggregations, and optimization strategies are all working as intended. Even a perfectly designed model can face bottlenecks or inefficiencies due to unexpected user behavior, incorrect configurations, or evolving data demands. That's why the next step is all about monitoring, measuring, and sustaining those real-world performance gains. By identifying potential issues early and adapting to changes in workloads, you can ensure your carefully built reports continue performing at their best. Let's dive into how you can measure those improvements and keep them going strong. Real-world gains, measuring and sustaining success. How do you know if your optimizations are really working? It's one thing to make adjustments that seem promising on the surface, but the real test comes when those changes are running live, impacting workloads and users. Without regular monitoring, even the best designed optimizations can slip into inefficiency over time. That's why tracking key performance metrics is essential, not just after initial improvements, but continuously. By monitoring query runtimes, resource usage, and error rates across your environment, you ensure that gains persist and adapt as workloads evolve. The best place to start is the Monitoring Hub, which centralizes the execution status of almost everything in Microsoft Fabric. Data flows, semantic model refreshes, Spark notebooks. All of these generate metrics that you can review in real time. For example, when you optimize a data flow using techniques like staging tables or fast copy, how can you confirm the runtime has actually improved? The refresh history in the Monitoring Hub breaks down every stage of the execution. You can see exactly how long the task spent at each step, how resources were used, and whether any errors occurred. This is like having a diagnostic tool for your entire pipeline. If a problem persists or arises again later, the refresh history provides a starting point to pinpoint where the issue lies. Another tool that many overlook is the Capacity Metrics app, available in Power BI for anyone running Microsoft Fabric. This app provides detailed insights into how your resources are consumed over time, broken down into two key areas, compute and storage. In the compute section, you can track capacity units spent across workloads, identifying processes or users that are monopolizing resources. For instance, a long-running direct query operation or an inefficient Spark notebook task might stand out on the usage graph. You can also track throttling and rejections here, which signal that a workload is exceeding the allotted capacity. These insights allow you to make informed decisions, like scaling up capacity temporarily or redistributing certain tasks. On the storage side, the Capacity Metrics app provides an overview of how much space is used across different workspaces. This is especially helpful after running maintenance tasks like vacuum and optimize on delta tables. After a vacuum operation removes unreferenced files, for instance, you can immediately see whether this freed up storage or reduced the file count in specific areas. Similarly, running the optimize function on partitions can prevent small file fragmentation, ensuring that files do not unnecessarily inflate storage usage over time. By keeping an eye on these numbers, you can quickly identify areas where intervention is needed or confirm that optimizations are working as intended. Let's look at a real-world example. A company using Microsoft Fabric to manage retail sales data had struggled with increasing query times and inconsistent report refreshes as their dataset scaled. Initial improvements, like better partitioning on their delta tables, helped reduce file fragmentation but didn't fully solve their performance issues. By leveraging the Monitoring Hub, they noticed certain refresh tasks, especially for daily sales reports, spent disproportionate time on data lookups. Digging deeper, they found that these queries were being throttled due to high capacity utilization during peak user hours. The problem wasn't just the query design, it was how resources were being distributed. To solve this, they made two adjustments. First, they scheduled intensive data flow tasks for off-peak hours. Second, they implemented aggregation tables for their busiest business periods, significantly reducing the load on the fact tables queried in real time. After these changes, the company used the Capacity Metrics app to monitor their resource allocation over the following weeks. It showed a clear dip in throttling instances and smoother capacity usage trends overall. As a result, report refresh times dropped by nearly 50%, providing more responsive dashboards for end users without further straining back-end systems. This example highlights an important concept. Optimizations aren't set-it-and-forget-it tasks. Changes that work today might not hold up tomorrow as your data grows or usage patterns shift. Sustained success depends on active monitoring and adaptation. For instance, even after partitioning and optimizing delta tables, new bottlenecks can arise if your data structure evolves or workload intensity increases. This is why tools like the Monitoring Hub and Capacity Metrics app are indispensable. They don't just identify problems, but also provide ongoing validation for the efficiency of your solutions. Continuous improvement doesn't necessarily mean creating entirely new workflows or rewriting pipelines each month. It could be as simple as rerunning optimized jobs on Delta tables that have seen heavy updates, or adjusting the retention settings in your vacuum operations. Because the optimize function is item potent, running it repeatedly won't waste resources re-optimizing files that are already compacted. Instead, it targets only unoptimized partitions, ensuring the process remains efficient. Similarly, when you shorten data lake storage retention policies used by vacuum, tracking the impact on overall storage through the Capacity Metrics app ensures that files critical for rollback functions don't get purged prematurely. It's not just about addressing active bottlenecks, but also anticipating future ones. The refresh history in the monitoring hub, for instance, doesn't just show current issues, it helps trend workflows over time. A data flow that initially takes 30 minutes to refresh may begin creeping toward an hour as data volumes increase. By catching this early, you can take preemptive steps like adding staging tables, enabling fast copy, or archiving historical data into separate Delta tables to reduce runtime. Without paying attention to these trends, what starts as a minor inefficiency often snowballs into a significant disruption. This kind of proactive approach isn't just a technical best practice, it also makes a measurable business impact. For users relying on Fabric-powered dashboards, performance improvements directly translate into better decision-making. In one success story, a logistics company leveraging direct lake storage saw improved query times for shipment tracking dashboards after restructuring their model using composite storage modes and aggregations. Their monitoring efforts didn't stop after initial implementation. Over time, as shipment data grew and query complexity increased, they started using the monitoring hub for detailed refresh history analysis and the Capacity Metrics app to keep an eye on resource usage spikes. By pairing these tools with periodic Delta table optimizations, they maintained the benefits of their initial efforts without regression, ensuring consistent performance even with higher workloads. The takeaway? It's not enough to simply optimize your pipelines or data models once. Long-term success comes from building a maintenance strategy that identifies and resolves inefficiencies as they arise, while keeping track of what's working. This isn't as daunting as it sounds if you integrate monitoring habits into your regular workflow. Scheduling periodic checks of the monitoring hub or reviewing capacity metrics weekly takes minutes but provides insights that can save hours of troubleshooting down the line. Monitoring doesn't just benefit SQL queries and data flows, it plays a critical role for semantic models as well. After optimizing a composite model with aggregations, analyzing query patterns in the monitoring hub can show whether those pre-calculated summaries are being utilized as expected. If they aren't, adjustments to model relationships or measure definitions might be needed to align usage patterns with the intended design. Similarly, direct query models demand constant vigilance via the Capacity Metrics app as they directly pull from the source database. Spikes in query failures or throttling alerts may indicate that it's time to scale backend infrastructure or refine your SQL queries for efficiency. Optimization can seem like a never-ending process, and in a way it is. But that's because your data and workloads are always growing and changing. Sustained success comes from treating performance management as a strategy, not a task. It's less about putting out fires and more about refining your system to minimize future risks. By regularly reviewing the monitoring hub, for example, users can proactively identify and address performance problems before they significantly impact their workloads. Likewise, leveraging the Capacity Metrics app ensures you're not allocating resources blindly. It's all based on data. The tools are already there for you. The monitoring hub shows you exactly where things stand in terms of refresh success, execution time, and sub-activity breakdowns. The Capacity Metrics app provides a high-level overview of resource allocation and usage trends. Together, they create a feedback loop that makes continuous improvement not just possible but manageable. And beyond just maintaining what you've built, these monitoring habits are directly relevant for the DP-600 exam. Understanding how to measure performance gains, interpret capacity metrics, and respond to bottlenecks demonstrates not only technical skill, but also the proactive mindset of an analytics engineer. Applying these techniques now will give you practical experience that's as valuable in real projects as it is in certification prep. Now, it's your turn. If you haven't already, explore both the Monitoring Hub and Capacity Metrics app in your Fabric workspace. Start small. Track the performance of a single pipeline or tune one report. Over time, you'll build the skills and confidence to manage large-scale systems with ease. Because just like optimization, learning is a continuous process, and what you master today sets the stage for what you'll achieve tomorrow. Optimization isn't a one-time task. It's a strategy for long-term success. As your workloads grow and change, small, consistent adjustments ensure that Microsoft Fabric stays efficient and resilient. By using tools like the Monitoring Hub, Capacity Metrics app, and Query Insights, you turn passive observation into proactive problem solving. Start applying these techniques today and take control of your Microsoft Fabric performance. Every adjustment adds up to better scalability, smoother workflows, and faster results for users. Stay tuned for Part 4, where we'll tackle the final steps to DP-600 certification excellence and bring everything together for success.